just to have that in the historical bounds. So now Laplace operator. We have a Laplace equation and we will have to solve the equation, which is a partial differential equation. Mathematicians are quite happy of partial differential equations because they offer them endless beauty of solving unsolvable. We will only take a small part of that and we will try to solve this equation in a one-dimensional case. Why are we doing that? Well, because the one-dimensional solution of this equation is very important to understand p-n junction in semiconductor. And p-n junction in a semiconductor is today quite an important topic in physics to get understanding of semiconductor devices, integrated circuits, and whatsoever. So let's get to this equation with the small change that we select a potential field which does not depend on y nor on z. So we have a field that depends on x coordinate only, and this field then produces a differential equation which is the Laplace equation in one dimension, and then it's an ordinary differential equation. That's not a partial differential equation but an ordinary one. So a one-dimensional Laplace equation would look like so we require that the second derivative of the function phi is 0 on the whole territory. Now to solve this, we can use a technique which is called successive integration. We can integrate and integrate again. So how? Well, first, we know from the equation how the second derivative looks. It's 0. Well, that's very nice, but we would like to find the function phi, not its second derivative. Okay, we can do that in the way that we integrate the equation, both sides of the equation, against x. So first, integrating this, we would get the first derivative of phi against x. That's the integral. And that is equivalent to a constant. We have integrated, and the result of that is a constant. Okay, but we already have an improvement. We have the first derivative, not the second one, but we would like to get the original function phi, and we successively apply integration. So the second time we integrate, we get the function phi on the left side, but on the right side we have cx plus another constant k. So now we have received a solution which has got two constants in it. When solving differential equations, this is quite common. You get several constants to achieve the result. So we have two constants, c and k. Now, I will rewrite this solution to a new sheet of paper and show you a case which can be solved by this method. So we have a solution, and we will somehow stick it to a simple task from electrostatics. So let's have two electrodes, two parallel electrodes, which are conductive One, let's say, is at a potential phi equivalent to 0. The other has the potential phi equivalent to V, which is the voltage. So we have the voltage between those two electrodes of V. And those two are also somehow located in the x coordinates, so that this has x equivalent to 0, and the other has the x equivalent to d. This is small d, not d, flux density, but the distance. And now we would like to find out the field in between those two electrodes, having those two conditions. Now, those conditions have a special name. For solving differential equations, we call those conditions boundary conditions. We have an area within which we solve the equation, and then the boundaries, the function we search for, has certain conditions, boundary conditions. There are several types of conditions. For us, let's take, we have prescribed the function value at the boundary, and let's try to find the function that would satisfy that. So we know that the function for potential must be of this form. Phi as a function x is Cx plus k, where c and k are constants. Now we will have to establish those two constants, and we will do that investigating boundary conditions. So let's say the first one, the left side, we have x equivalent to 0, and the potential should be equivalent to 0. So let's substitute that into the equation. We have 0, the value of the potential on the left side, is c multiplied by 0, the value of the variable, plus k. So we have 0 is 0 plus k, and for that we easily found that k must be 0. Okay, we have established one of those two constants. Now we have the second constant. We have to establish c. So we go to investigate to the other boundary. If x is equivalent to d, we would like to still keep the equation. So we have d of phi at d, which is v, should be equivalent to c multiplied by d. So we have v, the voltage, is equivalent to constant c multiplied by the distance d, and from this equation we easily find that we have c equivalent to v over d. Well, that's simple, and we can now write the final solution to this problem, which is the potential phi as a function of x is v over d multiplied by x. So this is the final solution for a Laplace equation in the case of two plumb parallel conductive layers or planes. First remark, we have solved this equation for the interior, that is, for the part of the space that falls between those two electrodes. This is telling nothing about the field outside. We have no solution for the field outside. So this equation holds only inside between those two electrodes. That's the first point. The second point, having this equation, we just could add two more equations for the inside. First, if we know the potential phi as a function of x, we could also establish the electric field strength, which is given as a minus gradient phi. So minus the first derivative of phi against x, because the derivatives against y and z are 0 from the definition. So we have E equivalent to minus d over d. We derived against x, obtained 1 unity, and then the flux density would be d So what we have found out is a homogeneous field at any point inside this region. There is the same value of electric field strength and the same value of electric flux density. So we have lines. Now let's find it out. The E and the D is oriented this way. We have the minus here. So the lines would be like this. This electrode would be positive. Well, of course, if V is positive. And this electrode would serve like negative. So there would be a positive charge over here and a negative charge on the surface of this electrode, provided that V is a positive number. Now the potential is 0 here, gets to V over here, and then there is a linear function. So this is the graph for potential phi. We have no information on the potential and flux density and field strength outside of the electrodes. So we have solved this simple equation. I would like to draw attention that we have been solving a differential equation, and we did in the way that we first have found a solution including constants. So that solution should fit any possible solution, and the fitting is done by adjusting the constants to fit that constants to the case we are investigating. We use boundary conditions and we set up the constants so that the solution fits our partial case with our boundary conditions. Ladies and gentlemen, we have completed the first part of this lecture. Now there will continue a short break. After that break, we will again meet at 5 minutes or at 9:25 and continue with a more complicated equation, which is not a Laplace equation but a Poisson equation, and we investigate a similar case. If you have any questions, think them over during the break, and we will start with the same sheet of paper with your questions after the break, after 10 minutes. See you in 10 minutes.